The high starting current of a compressor can be several times the running current, and a breaker or fuse size to handle the running current would open on startup. This is the reason for specifying a larger than necessary breaker or fuse. The reason the larger size is critical is that if the breaker or fuse is too large, it may not open quickly enough on a fault to prevent damage to the conductors. Even if the conductors are protected by the thermal overload in the compressor, opening the circuit quickly limits the amount of heat generated by the fault, which is desirable. The odd sizes specified on nameplates can be a bit puzzling. However, specifying a 45 amp breaker, for example, is more precise than specifying a 50 amp breaker because the manufacturer has determined that 45 amps is the maximum safe overcurrent protection for the circuit. Using a 50 amp or 60 amp breaker would allow the current to continue flowing for a longer time in the event of a fault, which could result in more damage. As a home inspector, you should always ensure that the overcurrent protection for an air conditioner matches the nameplate specifications. If you see a breaker or fuse that is larger than the specified size, you should recommend that it be replaced with a breaker or fuse of the correct size. Let's delve deeper into the reasons behind these specific breaker and fuse size recommendations. Firstly, the air conditioning compressor's motor draws a significantly higher current during startup than during its normal operation. This inrush current, often several times the running current, can cause a breaker or fuse sized solely for the running current to trip or blow prematurely, leading to nuisance interruptions of the cooling system. To accommodate this initial surge, manufacturers specify a breaker or fuse size that can withstand the start-up current without tripping, while still providing adequate protection against sustained overcurrent conditions. Secondly, the overcurrent protection device, whether a breaker or a fuse, serves two primary functions. One is to protect the circuit conductors from overheating due to prolonged overcurrents, and the other is to quickly interrupt fault currents resulting from short circuits or ground faults. While the compressor motor typically incorporates its own internal thermal overload protection to safeguard against motor overheating, this internal protection does not provide adequate protection for the circuit conductors in the event of a fault. The breaker or fuse, therefore, acts as the primary line of defense against these potentially damaging fault currents. Thirdly, the specific breaker or fuse size indicated on the air conditioner's nameplate is carefully determined by the manufacturer based on various factors, including the compressor's locked rotor amps, the full load amps of the motor, and the ampacity of the circuit conductors. This specified size represents the maximum allowable overcurrent protection that will ensure both reliable operation of the equipment and adequate protection of the electrical system. Using a breaker or fuse larger than the specified size can compromise the protection of the circuit conductors. In the event of a fault, a larger breaker or fuse may not trip quickly enough to prevent the conductors from overheating and potentially causing a fire. While it's true that a larger breaker will eventually trip under a severe fault condition, the delay in tripping can allow excessive current to flow through the conductors for a longer period, leading to insulation damage and increased risk of fire. Furthermore, the odd sizes often specified on nameplates, such as 45 amps instead of a more common 50 amps, are not arbitrary. They reflect the manufacturer's precise calculations to provide the optimal balance between accommodating start-up currents and ensuring adequate fault protection. Using a 50 amp breaker when a 45 amp breaker is specified may seem like a minor deviation, but it can reduce the safety margin and increase the risk of conductor damage in the event of a fault. Let's consider a scenario to illustrate this point. Suppose an air conditioner's nameplate specifies a maximum breaker size of 30 amps. The circuit conductors are rated for 25 amps, and the compressor's full load amps are 18 amps. If a 40 amp breaker were installed instead of the specified 30 amp breaker, the conductors would be vulnerable to overheating in the event of a sustained overcurrent between 25 and 40 amps. While the compressor's internal thermal overload protection might eventually trip the motor, the conductors could already be damaged by the excessive current flow. In the case of a fault, a 40 amp breaker would take longer to trip than a 30 amp breaker, allowing a higher fault current to flow through the conductors for a longer duration, potentially leading to more severe damage. It's crucial to remember that electrical codes, such as the National Electrical Code or NEC, are designed to ensure the safety of electrical installations and protect against hazards like fire and electrical shock. Section 110.3 B of the NEC requires that electrical equipment be installed and used in accordance with the instructions included in a listing or labeling. This means that following the air conditioner manufacturer's nameplate specifications for breaker or fuse size is not merely a recommendation, but a requirement of the electrical code. As a home inspector, you play a vital role in identifying potential safety hazards in residential electrical systems. When inspecting an air conditioning system, always verify that the breaker or fuse size matches the nameplate specifications. If you encounter a breaker or fuse that is larger than the specified size, document this finding in your inspection report and recommend that it be replaced with the correct size. Ignoring this seemingly minor discrepancy can have serious consequences, potentially endangering the safety of the occupants and the integrity of the property. Understanding the principles behind breaker and fuse sizing is essential for ensuring the safe and reliable operation of air conditioning systems. By adhering to the manufacturer's nameplate specifications and following the requirements of the electrical code, you can help protect against electrical hazards and maintain the integrity of the electrical system. Now let's talk about specific types of breakers. There are generally two main types of breakers used in residential applications: standard thermal magnetic breakers and ground fault circuit interrupter, or GFCI breakers. Standard thermal magnetic breakers use a combination of thermal and magnetic mechanisms to trip the breaker in response to overcurrents and short circuits. The thermal element responds to sustained overcurrents, while the magnetic element responds to instantaneous high currents, such as those caused by short circuits. GFCI breakers, on the other hand, are designed to protect against ground faults, which occur when current leaks to ground through an unintended path. GFCI breakers constantly monitor the current flowing in the circuit and will trip if they detect an imbalance of even a few milliamps, preventing potentially fatal electric shocks. For air conditioning circuits, standard thermal magnetic breakers are typically used, as they provide adequate protection against overcurrents and short circuits. GFCI protection is generally not required for air conditioning circuits unless specifically mandated by local codes. When selecting a breaker for an air conditioning circuit, it's important to consider the interrupting rating of the breaker. The interrupting rating is the maximum fault current that the breaker can safely interrupt without failing. The interrupting rating of the breaker must be equal to or greater than the available fault current at the point of installation. This information can typically be found on the breaker itself and in the manufacturer's specifications. In most residential applications, the available fault current is relatively low, and standard breakers with an interrupting rating of 10,000 amps are sufficient. However, in some commercial or industrial applications, the available fault current may be significantly higher, requiring the use of breakers with a higher interrupting rating. Another important consideration is the ambient temperature in which the breaker is installed. Breakers are designed to operate within a specific temperature range, and their performance can be affected by extreme temperatures. High ambient temperatures can cause breakers to trip prematurely, while low ambient temperatures can reduce their sensitivity. If a breaker is installed in an area with extreme temperatures, it may be necessary to derate the breaker or use a breaker specifically designed for high or low temperature applications. In addition to breakers, fuses are also commonly used for overcurrent protection in air conditioning circuits. Fuses are simple, reliable devices that consist of a fusible link enclosed in a protective housing. When an overcurrent occurs, the fusible link melts, interrupting the circuit. Fuses are available in a variety of types and sizes, each with its own specific characteristics. Time delay fuses, also known as dual-element fuses, are designed to withstand temporary overloads, such as those caused by motor starting currents, without blowing. These fuses have a time delay characteristic that allows them to tolerate short-duration overloads, while still providing protection against sustained overcurrents. Fast-acting fuses, on the other hand, are designed to blow very quickly in response to an overcurrent. These fuses are typically used in circuits where sensitive electronic components need to be protected. When selecting a fuse for an air conditioning circuit, it's important to choose the correct type and size for the application. The fuse should have a voltage rating equal to or greater than the circuit voltage, and its ampacity rating should match the nameplate specifications of the air conditioning equipment. It's also important to ensure that the fuse is properly installed and that the fuse holder is in good condition. A loose or corroded fuse holder can cause the fuse to overheat and fail prematurely. Regular inspection and maintenance of the overcurrent protection devices in air conditioning circuits are essential for ensuring their proper operation and preventing electrical hazards. Breakers should be periodically tested to ensure that they trip properly under overcurrent conditions. Fuses should be inspected for signs of damage or deterioration and replaced if necessary. The electrical panel should be kept clean and free of debris, and all connections should be tight and secure. By following these guidelines, you can help ensure the safe and reliable operation of air conditioning systems and protect against electrical hazards. Remember, when in doubt, always consult with a qualified electrician for assistance with electrical installations and repairs. Electricity can be dangerous, and it's important to take all necessary precautions to protect yourself and others. Finally, to summarize what we have gone over, firstly, understand that AC compressors have high startup currents. Secondly, correctly sized breakers protect conductors. Thirdly, nameplate specifications are code requirements.